Okay, morning everybody. One of your colleagues asked me to check on the past exam papers. I'm told by the admin, although I haven't checked it, that there are 2 past exam papers on the blackboard under the past exam papers link, and the third one, which is actually last year's, the 15-16 one, they're going to put up shortly. So there should be 3 papers in total on the link.
Yeah, actually there is 2, but one of them is blank.
Oh, can you remember which one?
14, 15, I think 13, 14.
13, 14 is a blank. Okay, I'll try and find out why. It's the trouble with these electronic systems. The other thing to say about the exam paper, I guess, is it will have the same structure as previous papers, but 1 or 2 of the questions might be a little bit different because my colleague is new to this module and may decide to change his material a little bit. So my bit should be quite similar, but his bit might have a few interesting twists to it, little extra challenges. So it'll be interesting to see what he does. So at the moment, the paper is divided into section A, which is theory, and section B, which is applied. My colleague's going to teach most of the applied. The only exception is this bit here, where I'm going to try and give you a bit of theory on CP and then also give you some practical information about CP. I appreciate in the audience there are probably people with significant practical knowledge on CP, so you'll have to just keep me right, okay? This is going to be a composite feedback system, so hopefully we'll all learn something. Right, and then I've got this slot and 3 others left. I'll see how the time goes. I may finish before the 4 slots are up and my colleague will take over. Right, so what we're going to do is talk a bit about cathodic protection. I'm going to talk about, remind you of some of the theory, and then we're going to look at some of the factors that need to be considered in actually designing a real CP system. The problem is that all our pipelines are exposed to some sort of environment, whether that's seawater, either because the pipe is lying on the seabed or buried in the seabed, or it's exposed to soils. And we've already talked a little bit about microbial corrosion. Is it aerated? Is it deaerated? Is it wet? Is it dry? We've also talked about stress corrosion cracking in terms of near-neutral and alkaline SCC. So is the soil acidic? Is it alkaline? These sort of factors all affect the pipeline. And so we need to try and protect the pipeline to some extent. See, we've got SCC and other things. The next little bit is a little bit of potted history, which you don't need the details of. It's just for interest. Really, the concept of cathode protection started with Humphrey Davy in the 1820s, and he was concerned with the marine environment where he was trying to protect one metal by galvanically coupling it to another. Since then, we've developed more sophisticated systems, so we've moved away from sacrificial anode dominated systems to cathodically controlled systems, applied potential systems. And that really came about because of the pipeline developments initially in the US, where steel pipelines started up, and then later on in the UK, as we started changing some of our infrastructure, which had cast iron pipes to steel pipes. And as we've got more sophisticated with CP, applying potentials to systems rather than just using sacrificial anodes, then we're getting wider applications on a variety of structures. So, as I say, you don't really need the details of that. It's just to say this is the development strand that we went through. So, we've got these pipes. They're exposed to environments that are aqueous at times. They may have microbes in them. They may have stresses applied to them because of the pipe pressure and so on. So you might get cracking, you might get localized attack, coating defects. There are lots of things happening. How do we try and limit the amount of corrosion? And we do that by inducing a cathodic potential on the pipe or structure, and there are two options for that. Either the galvanic corrosion option, which we talked about before, a sacrificial anode, or the use of an impressed current from a power supply. And all the basic corrosion cell rules apply. You've got to have an electrical link between the anode and cathode. You've got to have a sufficiently conductive electrolyte between the anode and cathode to complete the circuit. Okay, so it's a corrosion cell flowing in reverse in a sense. These systems that apply to pipelines, being large structures, are generally in association with a coating. Small components sometimes not so, but large, long lengths of pipe generally with a coating. And that's to get the currents down to something realistically generatable by the anode system that you put in. What you've got on your handout is this graph, which just quite nicely illustrates some economic aspects of the quality of the coating going up to a really high quality, perfect coating, and the cost goes up as the quality of the coating goes up. You just do a quick sort of rough tar paint. It's much cheaper than doing a proper polymer coating. And then the cost of the cathodic protection. And the cost of the protection decreases as the coating quality goes up. That's a sort of snapshot in time. What of course happens with your system is that if you plot current against time, then as the coating degrades, the current goes up. So you'll start off probably with a fairly low current, and it'll begin to climb with time as you get more defects in the coating. So ideally you want to be operating somewhere over here, but in practice with time, things happen to your structures, and you end up operating further over here. Okay. Let's just go back and remind ourselves exactly what's happening in terms of the corrosion currents and potentials. So when we put a bit of steel into an environment, it has a natural free corrosion or open circuit potential, E core. And if we then influence that position by supplying the system with electrons, then we'll increase the cathode process and decrease the anode process. So the structure at equilibrium has an anodic current flowing through at that free corrosion potential. And the magnitude of that current can be influenced by changing the potential. We'll talk about the magnitude of the potential later on, but you don't necessarily want to get to a position where you've got you want to significantly reduce the corrosion. You don't necessarily want to actually put so much energy in that you stop it entirely. There's a cost issue in some situations. So sometimes we are just limiting the anodic reaction, sometimes we actually stop. This diagram is on your handout, and what it's trying to show is the effect of changing the potential. So here's the free corrosion potential, yeah, and there's the free corrosion current, the dashed line down here from D. Okay, so that's your free corrosion. If you move the potential from the free corrosion down to position EA, you're actually at zero current. Yeah? This is zero here, and this is increasing current that way. So you move I-core down to zero. So when E reaches EA, then the anodic current is zero. If you then move the potential down to A, then a current B is still flowing, that dashed line there. And so you've still got some anodic current, which is given by the length AB, plus an applied current, which is given by BC. So this is your cathodic protection current, and this is your corrosion current. Okay? And so you've got a balance between those two currents and how far you drive the system down. The more current that you apply to the system, BC, the more expensive it gets. And the more possible problems you have interfering with neighbouring systems and so on. We'll talk about that later on. So even going down to this potential here, we've made a significant drop in the corrosion current, which will significantly extend the life of the pipe. Okay. This is all done with straight lines. This is a sort of Evans diagram approach to what goes on. In fact, there are always resistance effects, and there are always equilibration effects, which means you get curved plots. This is essentially the same thing. It's not on your handout. You don't particularly need it. What I just want to highlight is this bit of curvature here. So just imagine on your handout, on your previous slide, that as the current begins to approach zero, then the potential goes on this little bit of excursion, goes on a curve rather than a straight line. Okay, but it's exactly the same thing. Here's the free corrosion potential and the free corrosion current. So that's the free corrosion current, there's the free corrosion potential. And if you decrease the potential to E prime, then the current becomes less, the corrosion current becomes I prime, and your applied current is this distance here. So it's the same diagram, but just with a little bit of reality thrown in to indicate that you get some curvature of the potential current curves as you approach zero. And of course your oxidation line and your reduction line, in this case oxygen reduction, which is your most common cathodic process. Okay. What you have got on your handout is this diagram, which is to remind you that, of course, with the oxygen reduction reaction, we've got about 8 parts per million oxygen in the solution, in the groundwater or in the seawater, probably less in the soil actually. And so there's a diffusion limit, there's a mass transport diffusion limit for the oxygen. Fixed law of diffusion, the oxygen will migrate down the concentration gradient to the electrode. What that means is instead of the reduction line going straight on, which is this dashed portion here, as you change the potential, eventually you can't get the oxygen to move any faster to the electrode, and therefore the current peaks out. So you can reach a maximum current related to the diffusion of the species. With that current being smaller, that means that the values for E-core and I-core are depressed. They were up here and now moved down here. So the potential of the electrode changes because it begins to run out of oxygen for the cathode process. The corrosion current is smaller. And similarly, the protection current required becomes smaller. So as soon as you've got some limit in the mass transport, that means you need less current for the cathodic protection, which is good news. Good morning. You missed the best part. Are you all right?
Yeah.
Good. Okay. If it gets past the half hour, I don't let people in. I have to tell you, you're about a minute shy of being told to go home. Okay. So you've got a corrosion current, and you're offsetting that with a cathodic protection current. We're going to look at both systems. We're going to look at sacrificial anodes, and then we'll look at applied potential systems. So let's think about the sacrificial anodes to start with. Yes, sir.
With the limited,
Yeah, with the so your mass transport limited, so the oxygen diffusion goes off like that. Yeah.
it looks like you got a much better ratio reduction of corrosion current to apply for?
Just go back.
You get a better benefit than a non-limited.
Well, E-core and I-core are depressed. When you move to E prime, then you're right. On this diagram, you've got about a 50-50 ratio of applied current to corrosion current. But you're actually trying to reduce the corrosion current. You want that to be small. So.
Well, no, it looks like it'd be beneficial to have a restricted distribution. Again, you get more.
Yeah. Yeah.
Yeah.
The things are better because do you remember when we started we were saying the anode reaction can only occur as fast as a cathode reaction. If you limit the cathode process, you limit the anode process. So yeah, it is good news looking at a real system as opposed to an Evans diagram. Yeah, you're right. Okay, so you rarely use a single anode, you usually use multiple anodes on your structure. Zinc is used in pure form quite often. Aluminium is usually used as an alloy, so it's quite often some sort of aluminium zinc indium alloy, or some other mix, sometimes magnesium aluminium alloy. So you've got multiple anodes on the system. You need to secure them to the system. So quite often they're bolted onto the structure, and we'll talk about how you put them on pipes shortly. You need to be able to test the potential on the cathode, and so you need test points where you can get a voltage copper sulfate electrode potential measurement against the pipe, and they're usually located equidistant between the anode groups. And the sacrificial anode systems are predominantly for control of small structures in comparison to the CP structures, which can be hundreds of kilometres of pipeline. Okay. This is this on the handout? Yeah, this is on the handout. It's just an image showing you a typical system. So the current flow is going from cathode to anode, which means the electron flow is going the other way. Yeah, so electrons are generated at the anode and go around to the cathode, which is the pipe. There's a relationship between the spacing of the pipe and the anode. This says 1.5 meters minimum. You don't want the anode too close to the pipe because of the issue of throwing power between the electrodes. So you don't want too intense current flowing over a short distance between pipe and anode. You want to spread the current out across a longer section of the pipe. We'll have a look at the anode bag in a minute. What you've also got on here are the contacts to the pipe, and they're quite often thermit welded to the pipe. So instead of a conventional weld where you can get weld defects that might be corroded, that might be reactive, you quite often use the thermit process instead, and that's a process where you use iron oxide and fine aluminium powder, and you ignite it, and the aluminium reduces the iron oxide to iron, generates a load of heat, and that allows you to generate molten iron, which you can pour straight onto the joint. And this is in fact what they use on railways to join railway track together. The advantage of it is you get a cast structure, and it's quite corrosion resistant. It's a good quality, it's like a good quality weld. Okay, very few, it doesn't have the defects and microstructure and susceptibility to corrosion. So that's why they use the process. It's not that they couldn't get a portable welder, it's just it gives you a better finish to the system. Okay, so you've got good electrical contacts here, you've got a test point somewhere up on the surface, and you've got your anode buried a reasonable distance away, and we can talk about distances and so on later on when we look at the design stage of things. Okay. Here are some typical sacrificial anodes. What I've got is an old spent anode, so this one's dissolved away, okay, depleted galvanic corrosion, sacrificial anode. This is a new anode before it's been installed, okay, and it's simply a rough casting. Okay, we're not going to spend a lot of money extruding some fancy surface polished, we just cast a lump of whatever it is. This is the next stage, and that is to start to coat it, and we coat it with a conductive bentonite clay, and then we put it in a bag. So this is just a cloth bag. Here's the lead coming out of the top of the anode, and that's ready to bury in the trench. So one of the advantages of the bag is we've surrounded the anode with some conductive material, sometimes called a depolarizer, but it's aimed at trying to enhance the flow of current from the anode. Flow of current to the anode, flow of electrons away from the anode. And this is a trench. They vary somewhat in depth and size, and also in how they're backfilled. Rather depends on the soil conductivity. Okay. The advantages of the system is you don't need a power supply, which is really good news. So you can use them in remote places, crossing deserts or continents. got lower installation costs because you're not requiring some sort of power supply unit. You've got less wiring. You're simply bolting blocks onto offshore structures or putting anode bags in trenches next to onshore structures. The maintenance is lower. You'll see with the CP system later on that you need more monitoring. In this situation, providing you've calculated out the correct density of anodes, you just set it going and that's it. The voltages and currents that you get from sacrificial anode systems are lower than you get for CP systems, and so you get less issues with stray current effects. As soon as you get into urban area or areas where there are multiple buried pipes and multiple structures, then you've got to worry about stray currents. And the system is fairly controllable. You can add more anodes if you need to. So there are the main advantages of the system. The disadvantages is the limited driving power. So typically up to about a volt and up to about 5 amps current. So this is small potatoes in comparison to the powered cathodic protection systems. So because you've got a low driving voltage, remember our galvanic series, selecting the potential difference between the iron and the aluminium alloy or zinc, then this sort of system doesn't work very well if the resistance of the environment is high. So you need, it works fine in marine environments, when there's a high conductivity saline solution. It works fine in reasonably conducting solids. You may need to be in to replace the anodes, depending on what ratio of anode to cathode size you've selected in your initial installation. One of the issues, and it sounds daft, but there's much more obvious installation facility in a cathodic protection system with an applied current, because you've got a power supply and maybe a mains supply to that rectifier, and more test points and so on. It's just a bit more apparent there's a system there. And so when somebody's coming in to look at their other pipe, which might be crossing yours, occasionally people do odd things and ruin your system while they're working on theirs. So it's not quite so apparent, it's more discrete than the impressed current system. Okay. So that's a snapshot of the sacrificial anode system. We're now going to have a quick look at the impressed current system. Yes, sir.
So, like for example, for about maybe a 10 kilometer long of pipeline, what amount of cathodic protection do you usually?
Okay, so what you've got to do is try and achieve a control potential, and that there are standards for that, ISO and NORSOC standards for that, which we're going to talk about later. But you want to get down past about minus 850 millivolts copper sulfate. But we're going to talk about potentials and design of the system later. We're just getting principles at this stage. So we'll look at the anode materials in a little bit more detail later on, but I'll show you a couple of, these are just, they're not for pipeline, they're actually for marine application, small ships. And the only reason why I'm showing them to you is I've sliced the ends off both of them. This is a solid one and this is a hollow one. And what you'll see is that the anode is actually made out of steel, but it's coated. So it's the coating that is exposed to the environment. And by slicing it through, you can see that the steel's on the inside. All your electrochemistry are surface reactions, so you can make a cheap anode for a CP system by using a cheap material to make it shape, and then just coating it in whatever. And quite often, this one's a titanium-based coating, but some of them are platinum-based. What you want is an inert anode, and they're expensive if you make them solid. Okay, so let's make them cheap. So we just coat a material, a cheap material, with the inert surface finish. We need a DC power supply, and we'll look at that again in a minute. We want to measure the voltages, and sometimes there's actually a feedback loop into the power supply on a more sophisticated control. Sounds obvious, but we need to insulate the leads from the power supply to the anode, and that's fine. But remembering you're burying these anodes, and that insulated coating doesn't want to break down or start leaking water into the leads, because you're just wasting current then. So it's important that the way you wire it together is in high quality, and you want to make sure that your connections are good to your structure, and source again the thermal welding on the pipeline, for example.
Excuse me.
Yes, sir.
I don't get what is the.
So I've cut the ends off those, so you can see that they've got steel, cheap steel manufacture. And then obviously you can't use steel as an anode for very long. I mean, you can use steel as an anode, but it will corrode away. So what they've done is they've coated the steel with an inert material, which in this case is a titanium-based coating. And that coating can behave as an anode indefinitely. Okay, so it's just to keep the cost of the anode down. You want it to have a large surface area, but you don't want to make it out of solid titanium or solid platinum or whatever, so because it's expensive. So you make it cheap because you know all the reactions occur on the surface of the electrode. So it doesn't matter what the centre of the electrode is made of. It can be made out of rubbish, as long as it's conductive. So this bit's cheap. The coating's expensive because all the electrode reactions are surface reactions. Yeah. Okay. And I think we've just about run out of time. I'll see you next week. Thank you.
Next week.
Yep.
Next week? Yeah.
I
Do you not want to see me next week?
No, I saw another lecture is coming.
Not till middle of March, as far as I know. Unless he's got. Thank you very much. Cheers.
So I would love to come back later to
Right. Yeah, have you got it? All right. I'm just trying to. I'll be. When have you got it? You have class number 3. I don't have. All right, you're free the rest of the day. All right. Well, I'll be in the office. I'm teaching 1 till 2. I've got a meeting at 2 o'clock. So if it was before 1 o'clock, that's possible. Sort of. Right. So sort of 12ish. Yeah, is that good? I mean, there's no panic if you're using it.
Let's
then
go.
Yeah, sure. Good. All right.
we submitted already, maybe so we probably gonna get it from our school information.
Yeah, yeah,
And
yeah.
I could send you a
Sorry,
separate
yes.
one.
But we're completely snowed under at the moment because we're starting to do all our exam papers. So there's a bit of a panic on this week. Next week will be better. I hope.